Welcome, everybody. Good morning. Welcome to the continuation of the second part of the lecture on cloud storage. So yesterday, we looked into what is called object storage. Object storage, an example is Amazon S3 for simple storage service. Another example is Azure Blob Storage. Every provider has a way to store objects. Today, we are going to look into a different form of cloud storage. This is called key value store, and I will explain how it's different from object storage. You could ask the question, is object storage a database? Is it a database, like a relational database? That was actually one of the questions you asked yesterday. For several reasons, the answer is no. First, because I explained to you the notion of data lake, that you just throw your files onto some file system and then you query them in situ, right? So this is different from a traditional database management system. But there are other reasons. And one very important reason is the latency. The latency of S3, Azure Blob Storage, and similar systems that can store large objects, up to 5 terabytes of data, pictures, videos, data sets, web pages, and so on, 100 to 200 milliseconds. It sounds small. It is actually not small at all. For database management system standards, 100 milliseconds is a lot. And in order to see that, you need to understand that typically when you access data, you have several requests, not just one, but several. Imagine you send 10 requests, one after the other, to a system like that. You already need 1 second. 100 requests, which isn't actually that much, that already takes 10 seconds. That's beyond interactive time. This is a reason why for classical database management systems, we have latencies closer to a single-digit milliseconds, right? It's much, much less than the 100 or 200 milliseconds of cloud storage. The second difference, I'm going to go back to that. The second difference is that in cloud storage, we saw that you can upload objects or files up to 5 terabytes. In key value stores, the limit is 400 kilobytes. What that means concretely is that you store much smaller objects. You're not going to store videos and pictures in there, right? You're going to store maybe a small object. We'll see the kind of format you can have, like JSON and so on, but basically data. The typical use case for a key value store is actually your shopping cart. When you are on an online store and you have millions or dozens of millions of people shopping on the same website, in order to store the shopping cart, this is more than enough, right? So this is the idea here. So this is cloud storage, S3 blob storage, and this is key value for key value stores, the one we will see today. Also, another remark that maybe I wasn't precise or transparent enough yesterday. Objects, files, for the purpose of cloud storage and key value stores, is just a sequence of bits. It's a sequence of bits, nothing else. We do not even care what there is inside. Videos, pictures, pages, data sets, we do not care. It's just a sequence of bits. What this sequence of bits is going to be is something we will see in a few weeks, right? With textual formats, binary formats, and so on. For today and yesterday, it's just a sequence of bits, so it's a black box, right? The model in a key value store is, as the name indicates, the same model. You have values, so they are called values instead of object or file there, but you have values associated with IDs that we call keys. And given a key, you can have a value or you can put a value associated with a key. This is actually not different from object storage. That's also the way it works, right? Notice how we start having several terms for the same thing. That's going to be the same for the entire semester. ID is the same as key for the purpose here. So I might say ID, I might say key. It's the same thing. Object, file, value, they tend to be used interchangeably. Why is that? It's just that there's different technologies, and in every technology, they come up with their own naming system. So you need a bit of flexibility here and be open to the fact that the names can change. The most important is that you understand the concepts, and then if you learn a new system, it's easy to just change the names, how it is called. Okay, so two differences. Much lower latency and much smaller objects. Unlike cloud storage, where you can actually have metadata about the objects, like who created it, access control, and plenty of properties that you can associate with it. It's not much, actually, if you compare to the 5 terabytes of the object, right? In a key value stores, you don't have that. It's really just the key and the value, and that's it. You don't have any metadata associated with the value. Okay, but the model, as I said, is the same good old key value model where you associate values with keys, objects with IDs, whatever you call it. From a computer science perspective, this is actually, what is it called actually, the data structure? The abstract data type corresponding to this? Yes? A map, exactly. This is a map. All right. So the API is not surprising because it's actually quite similar to that of cloud storage. It's get and put. You also have delete based. So you can get the value associated with a key. You can put a value associated with the key that you want. So that's very similar to yesterday. It's just that it's lowercase, and yesterday it was uppercase because these were HTTP methods, right? But you see the parallel here. All right, so get and put. More precisely, basically, yeah, what do I hear? No, because I'm too close. I need to look right here. So one little precision I need to give you is that actually this would be the simple API. There is one more parameter in that API that we need to add, and it will become clear today why. It's a context, meaning if you get a value associated with a key, you are also given a context, and you are supposed to use that context if you want to modify the value. You just take it and supply it as is as the second parameter of the put function. What that context is, I haven't told you yet. I will very soon. All right. So you can get a value associated with a key, or you can put a value in association with a certain key. All right. It is important to understand also, this is something general in the database literature. We distinguish between write-intensive systems and read-intensive systems. Right? So the write-intensive systems, it's the good old relational databases you've seen in the bachelor's lecture, right? So it's monolithic, you have an overhead, you maintain consistency and so on. In key value stores, you typically relax some of the constraints here because you simplify everything, just have a key value model. You have eventual consistency. What is this? It's what I told you yesterday. Remember the CAP theorem. We no longer ensure that every node returns the same result. You might have some inconsistencies. It's just eventually consistent. If you stopped updating the system, it would eventually converge to something fully consistent. It's aimed at performance and scalability. So this is write intensive in the sense that we are going to write and write and write a lot to that system. This is in opposition to read-intensive systems, which we will see later with data lakes and Spark and MapReduce and OLAP and so on. We'll also see that during the semester. This here is really a write-intensive system. Okay. Okay. And here you actually already told me what that is. It is a map, also known as associative array, but map would be the name of the abstract data type here, so of the overall model. We will have key value models and maps all over the place in this lecture. At so many places, it's just a mathematical abstraction, really, right? We already saw it with object storage, and now we have it again with key value stores. Okay, so now let's start going to the physical level. As you know, in a data center, there's plenty of computers. We call them nodes, the servers. And we have a few design principles for key value stores. The first one is called incremental stability. It's the idea that when you are in a data center, nodes come and go. It means that a new node might arrive and register and now be available to help out in the system, or a node may leave. The system should continue to work seamlessly as nodes come and go. You add them, you remove them, it shouldn't disturb the system. Incremental stability. Second, symmetry. All the nodes are equivalent, right? It's all the same node, as we said, plenty of cheap machines, right, in the cloud. Next, decentralization. We will see various architectures. We will actually see centralized architectures in the next few weeks. But today, it's a decentralized architecture, meaning that all the nodes are at least at the start of the system on the same level. All right, and it should be also resistant. Maybe resistant is not the right word, but it should be okay if the machines have different memory and CPU configurations, right? You might have machines with more CPU, machines with less memory and so on, and that's okay, right? It's supposed to still work nicely. So these are the 4 design principles. And on the physical layer, what we're going to have, and that's as a consequence, because it's almost a natural consequence of the design principles we've had, it's a peer-to-peer network where the computers can communicate with each other, right? The opposite of that would be a centralized architecture. All right, next, DynamoDB, the key value store that we are studying today, is based on a protocol that is actually older than DynamoDB. It existed before. It's called CORD. This protocol works on the logical level by taking the keys. So the keys are the IDs. You hash them. So who knows what a hash function is? All right. Okay. So I won't explain. So this is a hash function. You put it through a hash function, and you get 128-bit ID. Right. That's the hash of the key. What you do next is that you take all these IDs, all these hashes of the keys, and you logically put them in a ring. This is logical. It's not a physical thing in the data center. It's logical. So you arrange all of the possible bit sequences of the hashes of the keys on a ring, modulo 2 to the power of n, right? If you go all the way to 1, 1, 1, 1, 1, then the next one is all the zeros, right? So it's a ring, it's a modulo. You saw that in discrete mathematics, right? It's just modulo 2 to the power of n. All right. What you do next is that every node randomly picks a 128-bit hash, right? So technically, it wouldn't be called a hash because a hash is really when you put it through a function, right? But you just pick one of these values at random. You just use a random generator. And then what you get is that the nodes are placed logically, it's again a logical thing, on the ring, depending on the random sequence that they have selected, right? In other words, we just randomly put the nodes on that ring. And that's something that doesn't need any centralization to do. All right, if you have a large number of nodes, you would expect that it's kind of more or less, well distributed. Right? Okay, next, the way you place the nodes on the ring decides on who is responsible for what. It means that this computer right there, this node, is responsible for this key right there. So again, I repeat, we take a key, we hash the key and get a sequence of bits, 128. This is where it would be. And then we go clockwise like this and look for the next node. This is the node responsible for that key. If we take another key, hash it, and get this ID right there, this hash, we go clockwise and find that computer, right? And the same for this key would be here. This key with the hash here would be there. And that means that this computer there has the entire domain of responsibility of all the hashes all the way anti-clockwise to the previous machine. For whom is that clear? Right, okay. So again, these are the hashes. These are not directly the keys, right? We take the hashes. All right, we have a question. Yes, maybe you can throw the catch box. Oh, wait. Now go ahead.
Better? Yeah. So is there like a load balancing measure? So I don't know if it just happens to pick like very like numbers very close to each other, then the second one would barely have any domain of responsibility, right? So is there like a load balancing measure in place for that? Or I mean, I'm sure there is, but yeah.
So yes, indeed, you are correct that you have to make sure that it's more or less load balanced. And there are solutions that I will present in just a few minutes in order to increase the load balancing and make sure that it's evenly distributed. Because absolutely, you don't want everything to be concentrated at the same place. All right, so that's a good point. Thank you. All right, so now let's come back to the design principles. Nodes come and go. So what happens if a node comes and goes? Let's start with a node that gets added. So imagine a new node arrived that we added to the data center, right? And it generates a random sequence of bits, and this is where it lands. What happens then is that there is a redistribution of responsibilities. Everything there that used to be the responsibility of this node right there becomes the responsibility of the new node, and the node right here only retains this interval of sequences, right? So you see, that's dynamic. You just reassign the responsibility if a node arrives. If on the contrary, oh yeah, then you need a transfer, right? So this node will have to communicate with the new one and transfer ownership of the values associated with the keys, right? So there is here a flow of data from that node to that node as this one takes over. These nodes here are not affected. This is why it's scalable. Even if you have thousands of other nodes, this is really a matter just between these two nodes right here that need to communicate if somebody joins. Now, if we remove a node, what happens? Well, we just reallocate the values right here to this node right there, right? So let's start with the case that this node graciously exits. It means that it's giving a warning ahead, like, hey, I'm about to go. So then this node has a chance to transfer the values to that one, then leaves, and then this is the new domain of responsibility of that node right here, right? So this is how they come and go. Now we still have the case that there is a crash and the node just goes away. We will need to address that. We need a solution for that. Because of course, if the node crashes, you cannot transfer the data anymore. All right. Okay. Now, the way you address this, the case of a crash, is that instead of saying that a node is only responsible for the interval of hashes that immediately precedes it in the ring, you actually assign more of the intervals. For example, you could say that the node at the bottom here is responsible for the 2 intervals that precede it clockwise, right? So now you would say it's responsible not only for what it was already responsible of, right? So this is what it was responsible of. Now it's also responsible for this. So you duplicate the responsibilities, right? So it means that this node here is responsible for this interval of hashes and this interval of hashes. And now it means that this interval right there is handled by 2 nodes, this one and this one. So now you get the solution to your problem. If there is a crash, like this one goes away, it's okay because there's a copy of all the values here, right? So this is how you solve the problem. You can do it with an arbitrary number of ranges. So here it was 2, but you can turn it like 3 or n in general, right? In terms of order of magnitudes, the number of nodes on the ring is going to be hundreds or even thousands. It's a very large number, right? Of course, I wasn't going to draw 1,000 of these nodes on my slides, right? But it's actually a very high number of nodes that we have. So n can easily be 3, 4, 5, you know, without any problem. Okay, now there is this core protocol, but DynamoDB tweaked a few things that they changed compared to the core protocol. In the core protocol, you need a way of figuring out in a decentralized way where a key is, whose node is responsible for a key. Remember that it's decentralized. It's a decentralized system. So in the core protocol, you do it with jumps in powers of 2. So you basically communicate with nodes. So you first start with a random node. So you land on N8, for example, and then you're going to try a jump by 1 to see the intervals that they are responsible for, then by 4, then by 8, then by 16, then by 32. You double every time, and at some point you are going to land in the right interval, right? So this is how you discover. It's in logarithmic time, of course, as you can imagine, because these are powers of 2. This is the core protocol. But in DynamoDB, this is not how it's done. It's actually done by using so-called preference lists, and that's actually then in O of 1 from a network perspective. It means that instead of having this dynamic discovery by jumping in powers of 2, instead of that, every single node in DynamoDB stores preference lists. It means that for every key or interval of keys, the node is able to say, this is the list of nodes that are responsible for this key. Yes, we can throw maybe the catch box, or it's over there. So let me increase the volume. There you go.
Sorry, just why is it needed that node discovery process? Isn't it as easy as just computing the hash of the key? So instantly you would know which part of the ring it goes. So I don't see that part.
Yes, so that's a good point. So the first point is actually done. You indeed can directly compute the hash of the key. So this is something you can do even as the client, right? So compute the hash of the key. But then you don't know where the nodes are on the ring. This is something you don't know, right? Because it's fully decentralized. You don't have a specific central node to whom you can ask who is responsible for what interval. And remember that by design, whenever a node is joining or leaving, it's not telling the whole network. It's only interacting, with one single node. So the knowledge is all distributed. And the cost that you have to pay for that is that it's extra resources that are consumed when you want to discover where the keys are, right? Does it answer your question? Okay, there's another question. Let me increase the volume again. There you go.
Yeah, so node 8 knows basically the address of like node 32 and node 42 and something. So what happens if one of those nodes leaves abruptly? So I don't know, like node 8 knows the address of node 32, but then it leaves and we can't find it anymore. How do we do it?
Then I think there is some kind of resiliency. So if you have surprises like that, it's fault tolerance. So you just try again. If it doesn't work, you just initiate the whole thing again and find again the node who is responsible, right? Okay. It's designed to be fault tolerance, right? What's important though is that this is not how DynamoDB does it, right? This is the core protocol, the original one, but instead DynamoDB uses these lists, and then you immediately know on any node for any key which nodes are going to be responsible for which key. Of course, that's a logical view because there are so many keys that there's no way you can have the whole list, right? It's going to be organized by intervals and with some black box encapsulation, right? But this is the idea. So you can in O of 1, and I mean O of 1 in respect to the network, because of course in local computation, it's not O of 1, but except if you use a hash table. But basically that's the idea. Every node knows which nodes are responsible for every key and key range. All right. N is a, oh yeah. So let's go to Zoom. Can you maybe read it? You don't have a microphone. Yeah.
The question is, failures among nodes are generally highly correlated, like collocation, same cloud region. Will the duplication of range help?
Yes, it does. And there's another technique I'm going to introduce very soon with tokens. So this is something also where you will have an answer very soon to this question, right? Okay. So N is the parameter we saw earlier with the number of nodes responsible for a key range. And this is the length of the list of every preference list there. Okay. So the first one is important. It's an ordered list. The first one is the coordinator, the main node, and the other ones are just on standby in case there is a problem. Okay. And the idea is that then you have two other parameters, R and W, meaning that whenever you read a value, you ask for at least R nodes. R is a parameter. And when you write, you need a confirmation from at least W nodes. And you have a constraint on R and W, they must be chosen in a way that their sum exceeds parameter N, right? That's how the system is designed. And that's called a quorum-based system, all right? There will be the DynamoDB paper where you see even more details of that. So the way it works now, if I zoom out, is that there is a load balancing. So you connect to a random node with that load balancer. The random node will have the preference list. So it knows exactly who is the coordinator for a specific key. And you have, for reading more or writing more, you have also the addresses of the other nodes that are hosting the replicas. All right. So nice aspects of what we have is that it's highly scalable, it's robust against failure, it's fault tolerant, it's self-organizing, decentralized. But there's a few issues, is that it's lookup only. You cannot search a range of keys because it's all hashes, so it doesn't preserve any order. All you can do is look up a specific key, just one, and that's it. Data integrity, security issues is not really handled here, right? So it's extra layers of protocols, security issues that would typically be a Byzantine generals problem. So that's the blockchain. You basically go into Paxos and this kind of distributed systems. Here we assume you have full control of the cluster and security is not an issue. You trust all the machines in there. Okay, now let's solve a few issues. You already mentioned that. What happens if we have a concentration of nodes in the ring? That's going to be problematic because then there is this node here responsible for almost the entire ring. That's not okay. So that's an issue. The second issue is that if you spread them evenly, you do not do justice to the nodes that have more memory and CPU because they still get the same responsibility level. So how do you account for that? So we need a way to artificially increase the number of nodes in order to solve that problem because of the central limit theorem, right? The more nodes you have, the more close it will be to something more uniform intuitively. And the idea is that we are going to assign virtual nodes, tokens that we just distribute over the ring, but this is all virtual. And now the idea is that every real node, physical node, gets several virtual tokens, right? So for example, with the colors here, you have, for example, this machine right here is responsible for this and this virtual token. And that means that it's for this range of values and this range of values, right? So you just have an extra level of virtualization where you have virtual tokens and the nodes can get several tokens. The bigger computers get more tokens, the smaller computers get less tokens. This is how you distribute. And since you have many, many more tokens than machines, then the central limit theorem will help you have something more evenly distributed on the ring, right? And now if a node leaves, you just reassign the tokens to other computers. If a node joins, you just transfer the ownership of tokens from other computers. Yes, there is a question here.
Yeah. So I wanted to ask who assigns the number of tokens to each machine? Because we said that we wanted it to be a decentralized system. So who is the authority that decides that this machine gets 1 token, whereas this machine gets 8 tokens?
So for this, there are protocols. I'm not getting in the details of that, but there are plenty of protocols that are taught in distributed systems lectures. So there's a whole area of computer science dedicated to this. It's all about how do you synchronize and agree on something in a decentralized network, right? So this is out of the scope of the course, but you can see, if you, by the way, one of the most beautiful papers that was written is by Leslie Lamport. It's Paxos. You should read the Paxos paper. It's beautiful. It's really a jewel of computer science. But basically, so I'm not sure if that's a disappointing answer, but basically, yeah, that's out of scope for this lecture. But there's plenty of distributed system lecture that will go into details of that. So you just need to trust here that there is a way that in a decentralized manner, you can agree on these sort of things. Right.
And it uses one of the methods sort of like that solves the Byzantine generals problems, or is it?
No, that's a different thing. So here, so there are basically algorithms in distributed system that assume that you trust all the nodes, and there are protocols that allow them to agree on something. The Byzantine general problem is if you do not trust all the nodes. This is the case, for example, if you look at Bitcoin, Ethereum, and so on, all of the blockchain-based things, it solves the Byzantine generals problem in the sense that anybody on the planet can actually join and contribute nodes. So you have no way of being sure that all of the nodes are trusted and that nobody is modifying the code to run something else, right? But in that case, we don't have that problem. We can really trust that you trust all of the nodes in there. They are in your cluster, in your data center, military-grade protection, so nobody can alter that, right? Did it answer your question? Yeah. Okay, awesome. So now I have to tell you about vector clocks. This is in order to handle this eventual consistency thing. Whenever you update, you increase the version. So this is version 1, you have version 1, then you have version 2, let's say it's node A that coordinates, and then maybe A fails and B takes over, so then it's going to increase its own clock. So you see, you maintain a clock for several nodes, so B says 1, and C then maybe in some other part of the planet, because there was like an earthquake or something, C disagree and puts another version set to 1. And then the idea is that you reconcile the two when everything is fixed. And then you have a new, here, a new clock, a vector clock with 3, A increases by 3, 1, 1. This is a partial order, right? You can always check if a vector clock is higher than another vector clock, if and only if each one of the numbers is higher than the others, right? So that's the definition. It's a bit more formalized, more complex than that, but this is the intuition. This, in fact, is a clock compatible with special relativity theory. It would work in space-time. And that was, in fact, invented by a professor at ETH, Friedman Mattern. I don't know if you know who contributed, among others, the vector clocks. This is what we use in DynamoDB. We use vector clocks in order to keep track of the version of the values as they are changed and new values get uploaded, right? So the way I will give you plenty of examples, but now you know this is the context. The context I told you about is in fact a vector clock, right? So let's assume, I will give you an example, duplication factor 3. Every interval is handled by 3 computers. Let's assume, first it's empty, there is an incoming request. A client says, please put value A in association with key 1. And I'm only going to use key 1 for my example. I'm not going to use other keys, right? Just key 1. So a request arrives and say, okay, associate key 1 with value A. So you look up the preference list where you are from a random node, and then N1 is the coordinator and so on. So you put the vector clock set to 1 for N1, right? So that's the new context. And then you associate A, the value A, stored with key 1. I don't put key 1 because, as I said, we only do key 1, with the vector clock N1 with time 1. And then you duplicate, right? You replicate synchronously all the way to W nodes, right? And then asynchronously to the rest of the nodes, right? Okay, so now they all have, after a while, the copy. We wait until it propagates. And then somebody says, let's get the value associated with key 1. So you look it up here. You gather all of the versions. In that case, there's only one. They all agree. And then you return value A together with that context. Okay? Then the client says, okay, now replace A with B. So associate key 1 with B instead of A, right? So then you do a put key 1 B, and you repass the context that you previously got, N11, and now there's an increase by the coordinator, now setting the context to 2 here, and then you store B with a time of 2, right? So B, this is higher than A, so this is the latest value, and A is old now. Then you replicate and propagate. If you get key 1, then you will get all the values, but now you see there is a latest value here because 2 is greater than 1, so you only return B together with that context. Now, the client says, okay, that's fine. Now put C in association with key 1, right? Okay, so we increase the context, set it to 3, and so on, but this is like a Hollywood movie, there's a catastrophe, and before we could actually propagate things, there was a network partition. That's the P in the CAP theorem. So what happens is that we cannot propagate, and even worse than that, a client could actually connect from the other part of the world that's disconnected to N2, which is the interim coordinator for that part of the world, because they cannot access N1. So they gather the versions and get B. So you see, this is not atomically consistent, because here you don't see C, because you're disconnected from the part of the world that has the value C. So you get B. And even worse, to make it even worse, that client is say, okay, now store value D in association with key 1. So now you end up with a value D here, which is different than value C there. Now we restore the network, and the updates have not propagated yet. If you get key 1, now you are going to gather from all the nodes in the preference list, but now you have a problem because there is no, I will not ask the question, I will directly tell you in the interest of time. You have a problem with the order because there is no such thing as a latest version. There is not a single latest version. Could be C, could be D. Maybe it's C in America and it's D in Europe, right? So we have a disagreement. So this is called the partial order. C and D, so the two here are not in any order relationship right there. And the way that this is called, so the name of that in math is maximal elements of this partial order. They are not comparable. This is how you handle conflicts. And the idea is that if you get that, then you're going to get, if you get the value associated with key 1, that should be a key 1 here, not an A, you get both C and D. since there is no such thing as a unique latest version, you just get all of the latest version, formally, all of the maximal elements. Yes, there is a question. Maybe we can try to throw again the catch box.
Okay, so my question was, I see that in this case, when we return the context, we got rid of N12. That's because we always take the latest sequence number for an existing node, right?
This is correct.
Okay, I was just unsure and I wanted to check that.
So indeed, I forgot to explain that. Indeed, you could, of course, return N13 and N12 and 21, but for reasons, it's basically just an algorithmic optimization, because in order to compute the new context, all you need is the maximum values for each node. So this is why you merge the two vector clocks with a new vector clock that has all the maxes. It's really just an algorithmic tweak, let's call it that way, right? But this is a good point. Thank you very much for mentioning that. So now let's let it propagate. So since anyway it's all restored, we repropagate everything. And now we can even do a bit of cleanup by pruning the old versions, which anyway are no longer up to date. So let's only keep C and D. And now we have an incoming request with the context that was the last one we got, the one that you said was merged from the vector clocks. And it's the client's job to solve that. And the client said, okay, now I resolve the conflict between C and D, and I decide that the new value should be E. So let's put E in association with key one with my merged context. And now we increase, as always, that's the same protocol as before. N1, now there's a +1 right there because it's all restored the connection. So we have the coordinator online. We add 1 here, and now we have N4, right? So now we have N4. So what happened? We reconciled the two versions because you can check that this vector clock is both higher than this one and higher than that one. Now we have again a maximum and just one maximum, right? For whom is that clear, this thing with the partial order and the conflict resolution? All right, almost all of you, perfect. All right, so this is now, you can draw a version history with the vector clocks, which in general is what kind of graph? A directed acyclic graph, yes, DAG. So this is a DAG, as any partial order in mathematics gives you a DAG. Do we have a question? Maybe criticism?
Yes, question from the chat. So as a user of the DynamoDB, I am not guaranteed that the get key returns exactly one value. Is that true?
Yes, absolutely. Yes, you can have multiple values. In fact, whenever there is a conflict, you will get multiple values returned. This is what happened here. Here, you see you return C and D. This is because this is an example where there are several maximum elements according to the vector clocks. Then you return all of them. You basically make it the user's problem, right? You say, okay, there's a conflict, deal with it, and then come back to us and tell us how you solved it, right? And then later the user comes back and says, yes, now it's E. Is there another question on Zoom?
Yeah, there is another one. It's about, you explained before that we read and write such that the R plus W is larger than N. And what if, because of a partition, it is impossible to read from or write to that many nodes?
This would indeed be a problem. And in fact, this is why you need to think of how you set the parameters R and W, right? You need to be careful. Again, I need to remember that in practice, there's thousands of nodes. So even if there's a partition, maybe you're going to have 300 nodes on one side, and for now we are exactly on track. So in practice, if you have the material, I'm done with the section of cloud storage, then you still have more than enough load storage in order to write 5. But indeed, if you have a partition and you end up with a super partition, you would actually consider it as right. So the Hadoop distributed file system that will keep us busy, then it cannot continue working with because of W. And I'm checking if you follow to make sure that if it was too fast, I come back on some things, and otherwise we continue as planned. So that's great. We have a majority, and to be precise, 80% the formulation. So this is perfect. all right, so there are
in
exercise
advance
sessions today and next
three
week, mostly
values,
about
N,
using
R,
PostgreSQL.
and W.
Please double check
You
because the
must
TA
choose
team
these three
spends time,
values,
reconfiguring
respecting
the
the
groups. We have
constraint that
online
R
groups
plus
now,
W must be
thanks to
stricter,
Junhao and the team. So
strictly greater
check
than
again
N.
on eDots.
Once you
If the
have
time
chosen
of
these
the group
values,
you
you
are
don't
in has
change them
changed and
anymore.
just
That's
pick
it.
another
Then you
group
run
if
the
you're not
system.
happy with that.
And then
I hope
when
you
you
enjoyed
write,
the
you
exercise
make
group. If
sure
you have
that you
any
replicate
problems,
synchronously
contact
to
me
at
or
this
the TA
W
team. We are
node.
going
And when you read, you make sure that you get values
and
from
as far
at
as I'm
least R
concerned, I'll see you again next
right?
week,
Just to make
Tuesday at
the
2 in
terminology
CAB
precise.
for HGFS.
Okay, so
Thank
now
you
we
very
have
much.
the vector clocks. It's all reconciled. And I have a few last words before I let you go. So we have seen that there's Amazon and Azure and Google Cloud. In Amazon, the mindset is that they have plenty of services. S3 is one,
I have one more
DynamoDB
thing
is
to say
another, and there's probably
that I
100
forgot.
of them. This is
We
the
are going
architecture.
to set you up
In
for
Azure, the
Azure
mindset is a bit different. They
So
have
you will receive
bigger
an email by
systems.
John Howe.
For example, there's one
Today or
called Cosmos
tomorrow.
DB that tries
Please
to
be careful to
handle
read that email
several
and
things
follow
at
the
the same time.
instructions.
It's
While
about
on
Azure
Amazon, you would have
subscriptions.
one here,
Thank you.
one here, one here, one here. So you see the mindset is a bit different, but the main ideas are the same between the providers. So there's 3 takeaway messages for today. Simplifying the model, that's the key value model with IDs associated with objects. We buy cheap hardware. This is what there is in the data center, plenty of cheap machines. And we remove the schemas. There was no such thing as a relational database today, right? It's a physical, low-level thing. You basically throw everything at the user. It's the user's job to then rebuild everything. But in fact, in the next 12 weeks of the semester, we will be building plenty of things on top of cloud storage and so on. All right. I have 3 more minutes to just check that you have been following.
Yeah, you want to impress us
So hopefully, there we go.
because now like it's a little bit over.
I need to re-click.
But I think it's in Friday.
It's right here. So just checking if you followed. For now, we are exactly on track regarding the material. I'm done with the section on cloud storage with S3, Azure Blob Storage, and DynamoDB. Next week, we will look into HDFS, Hadoop. Who heard of Hadoop? Right, so the Hadoop distributed file system will keep us busy next week. And I'm checking if you followed to make sure that if it was too fast, I come back on some things, and otherwise we continue as plans. So that's great. We have a majority in the 80% plus buckets. So this is perfect. All right, so there are exercise sessions today and next week, mostly about using PostgreSQL. Please double check because the TA team spends time, reconfiguring the groups. We have online groups now, thanks to John Howe and the team. So check again on eDots if the time of the group you are in has changed, and just pick another group if you're not happy with that. I hope you enjoyed the exercise group. If you have any problem, contact me or the TA team. We are going to be happy to help. And as far as I'm concerned, I'll see you again next week, Tuesday at 2 in CAB for HDFS. Thank you very much.